Hi there. My name's Isaac Jimenez, and I will be giving some context to some of the problems that we will be solving. So, in the past, America outlawed discriminatory practices preventing marginalized voters from exercising their right to vote, meaning that there were forms of voter manipulations that were preventing a certain type of voter's voice from being exercised. And we need to figure out a way to reduce the bureaucratic restrictions we currently have. So, voters are currently have a physical way in which they can vote, so they must go to the voting polls and write in their ballots or use electronic voting machines at these voting polls. And in some states, they can mail in their voting. So we need to modernize our electronic voting systems, which allow voters to vote from home. So every voter has an option in which they don't have to get the day off, wait long lines, or if they're not able-bodied, can still exercise their democratic right and have their voice be heard. And through all these options, we will encounter a security issue and voter manipulation issue. So figuring out a way in which voters can just vote from the comfort of their home provides two big problems. We need to figure out, how do we secure the voter data? How can we tell that the ballots have been validated and whether the voter starts off their ballot process in their phone and then finishes it off through a laptop? And another problem is we need to figure out a way in which we track the voters so we can tell whether they have been manipulated through their social media feeds or how they engage with content online. Our solution is creating a website in which we can use forums for vote registration. The users can go in and check their voter registration status, as we will be migrating data from the state's servers. So that way, it's one central place for voters to see whether they need to register to vote. We would also be handling voter registration, the ballots, and using sessions, we would capture whether a ballot has been completed or not and whether it's been validated. So voters can go from their iPad to their phone and pick up where they left off. This website would also be aggregating news through using APIs, as we have different forms in which we can track these voters through IP address, MAC address, and cookies. So we can see the engagement between the news articles, but we can also incorporate social media logins to be able to capture their social media handles so we can see whether there has been any external voter influences. All right, so how are we going to get this application to work? Well, after much talk, Kyle and I ended up settling with Amazon's serverless cloud technology. So, Amazon already has multiple contracts with the military and other areas of the government. So, we know that they can deliver in security and scalability, which are essential for our application. Since we'll be tracking voter influence, meaning that we will have many data streams in which we will be fetching from either social media APIs and also their engagement outside the app, which we will need to capture all the content. So we will be using Kinesis Data Firehose that will then be using Glue, which will extract and transform and catalog a lot of that metadata. From there, we will be using SageMaker, an AI training tool by Amazon, which will help us in checking security and monitoring the content and helping us analyze and digest whether a voter has been influenced from their engagements outside the application. And finally, we would be using MongoDB, which will help us in creating SQL-like queries so we can help further understand our data.
Gathering voter data on our metadata was grouped into 6 main categories: metadata on device, metadata on web data, ad monitoring, APIs of social media and news websites, and HTML of web pages and printed media. Our metadata on devices includes IP address, MAC address, and timestamps to measure the duration of a user session. We identified a voter's device type, operating system, browser, and a device location using IP geolocation. Our metadata on web data includes the website name, website session duration, using timestamps and timestamps gathered on the user's posts, their likes, comments, reposts, and post visits. Our ad monitoring processes involve who posted it, the ad company's name, their authors, the timestamps of the posts, and what method was used to post the ad. All available social media APIs are used via an API key to access data. If API keys are not available or do not fit our search criteria, we use web scraping technology to gather parsed HTML data, in particular from news sites and political blogs or any other website on the internet which contains content related to political and social topics. To gather information from printed media, we use a scanner to digitize the physical documents and then convert them to digital images. We then convert the scanned images to machine-readable text. Text is extracted from the digital documents to perform natural language processing, which analyzes the data for the extraction of political and social view text entities. Sentiment analysis and topic modeling extract data for additional context. Lastly, text classification separates our documents into categories. Securing our voter data and metadata involved using the most modern and advanced data encryption algorithms available. This ensures our data preserves its integrity. Controls are in place to protect against intentional alteration by unauthorized parties as well as unintentional alterations due to any fault in transmission processes. Digital signatures are used for all data transmitted to ensure it was not altered in transit. This includes data at rest, which is all of our storage devices, including our storage area networks, data in transit. This is our data which is transmitted over a network, wired or wireless, on internal networks or public networks. And lastly, our data in use is any data we are using an application for example, SageMaker machine learning analyses. To meet our standard of data integrity, our encrypted data uses fully homomorphic encryption. This allows computations to be performed on our encrypted data without first having to decrypt it. Our data computations are always in encrypted form, and when they are decrypted, the result is always identical to computations that would have been done on unencrypted data. This preserves the privacy of our data in storage and while being analyzed. No attacker would be capable of gathering any meaningful information out of our sensitive data at any stage in our storage, processing, our data in transit to any of our cloud services. In the unlikely event of our system being compromised, our data would always remain in secure form. Lastly, our system admins and engineers undergo extensive background checks. Authentication and access management procedures are in place that meet or exceed industry regulations. To facilitate our API keys, we chose to use AWS API Gateway. First, we target social media APIs and news APIs and simplify this process using AWS API Gateway. Throttling and monitoring requests to our database storage optimizes our system performance. Implementing managed caching to store API responses further streamlines and expedites our API calls. We use CloudWatch to reduce latency and provide DDoS protection on our API calls. Our gateway configuration feeds our API data to Kinesis. Once ingested by Kinesis, data is extracted, transformed, and loaded by AWS Glue and stored in our MongoDB data center. For our web scraping purposes, we chose to use Python's Beautiful Soup. In this example, a Python script scrapes the data from a social media site. We create a function, set a URL, and use a GET request, and use the library's HTML parser to extract the information we want. The data is formatted to a JSON file, which is then encrypted and sent to a Kinesis Firehose pipeline. We use AWS Glue to move our data. AWS Glue is a serverless solution for our ETL processes. For our usage, the first step is scraping the targeted data from the website. This data is then encrypted and stored in AWS S3 bucket. Next, a Glue crawler is created that traverses the S3 bucket, creating metadata tables in AWS Glue Data Catalog. In the next step, a Glue job is created to extract, transform, and load data from the S3 bucket. The MongoDB connection is configured using its URI along with authentication credentials. A target Mongo collection is specified and the data is written to the database. Our Glue jobs are scheduled to run at 15-minute intervals. In the last part of the process, CloudWatch monitors our Glue jobs and logs any errors associated with processing the data. We chose AWS Kinesis Data Firehose for our streaming data. Data Firehose delivers near real-time streaming data to our ETL processes and to custom HTTP endpoints to our MongoDB database. We configured data producers that send the data to Firehose. This data is automatically delivered to our ETL and MongoDB configurations. Using Firehose provides us serverless data transformation and automatic scaling, which gets our data delivered to our destination services within 60 seconds, allowing us to access our data to quickly clean, categorize, and store it for further analysis.
From the application outline, you can see that Glue is an essential component for making this application work. It is an extract, transform, and load service by Amazon. as it uses data crawlers throughout the application to see if there's any changes or any new data and extract it automatically as it generates jobs automatically. So let's say that in Kinesis Data Firehose, we have new data streams. It just extracts it. It can transform it it uses Spark under the hood to clean the data. And from there, it can take it to S3, which can be an object store, where it can catalog the data. So let's say if you had a library and you had uncatalogued books, then it'd just take longer for you to find the book that you're looking for. So that's why cataloging is important here. And then one possible concern is that we're only have one data catalog per region, and this is more of a Amazon design, and we will be working closely with Amazon to help figure out any potential security issues that can come with having one data catalog per region. Amazon CloudWatch allows us to monitor applications and resources in real time, and we can set up alarms in which can let us know whether there's suspicious activity like a DDoS attack or unauthorized access. And then through this monitoring, we can log the records of actions which can help in auditing investigation of voter fraud. And even though these data centers are distributed regionally, as we only have access to like one catalog per region, we can use CloudWatch to monitor multiple regions and also help in finding resource inefficiencies, which can help in managing costs. There's going to be so much content from data streams that it's going to be humanly impossible for a team of analysts to digest. So we need a new modern solution in which we use SageMaker, which is an AI training model component within Amazon's infrastructure that can help us in digesting the user's opinions. So since we're tracking all the engagements and social media posts, we can use this AI to train and figure out the general sentiment of the voter. It can also help us in figuring out any voter fraud detection through monitoring any registration inconsistencies. It can help us in predicting voter turnout, where we can gain insight into the possible socio-economic factors that prevented voters from voting. And ultimately, this training model learns and gets better over time, meaning that in the future, we will be able to detect new tactics much quickly. And we can use this training model in other types of elections.
We chose MongoDB for its fast storage and retrieval capabilities. JSON documents in their binary JSON representation allow efficient storage and fast retrieval. Not having a fixed schema allows our key value pairs to have varying structures. This fits with our approach of using a dynamic data model. This allows records to have attributes that other records lack, allowing its flexibility in our data retrieval. Our lookups alleviate the complexity involved in SQL indexing. Our indexing methods pertain to the keys themselves, which optimize the process of locating our desired values. In this example, MongoDB queries social media clients who have logged on to the social media website with a mobile device. This information is helpful because it shows that this voter is capable of using a mobile device to access the web. We have taken into account that there are populations who are not capable of using a mobile device to access the internet, and knowing the percentage of users who are adds a useful component to our analyses pertaining to accessibility.
Here's another example in how we can query the data in our MongoDB. So since MongoDB stores a lot of the data in collections, we can use lookup, which is kind of like the equivalent of joining two tables. So here from the example, you can see that we start off at the ballot section and are joining from the voters and connecting them through the voter ID. And the output is a merged voter ballot collection, essentially. And from there, we go to the next stage in which we are searching for users where they didn't have a valid session. And from there, we can find the exact users and extract the user trackers that we implemented in helping in monitoring potential voter fraud investigations.